is Margrét Jónsdóttir. Sorry, it's a bit challenging to pronounce your name. So Margrét is a final year PhD student at University College Dublin, Ireland. She is due to submit her thesis next month, and the title of her thesis is Database Stochastic Modeling for Short-Term Dynamic Analysis of Power Systems. Margrét will do a video presentation, so the floor is yours, Margrét.
I'm Margrét Jónsdóttir, and I'm a PhD student at University College Dublin. Today I'm going to be presenting our paper titled Stochastic Modeling of Tidal Generation for Transient Stability Analysis, including a case study based on the all-island Irish transmission system. Currently, the renewable energy in Ireland is almost entirely composed of wind generation. However, in the sea around Ireland, there's a huge untapped potential for other energy sources, and specifically for tidal generation. This brings us to the objective of this paper, which was to provide a comparison of these two renewable energy sources, that is wind and tidal generation, when it comes to the dynamics of power systems, specifically in the case of the Irish system. Since tidal generation is not that well known, I thought I would start with a brief background on tidal generation. So tidal turbines extract energy from the ocean movement due to the tidal phenomena. The tidal phenomena is due to the sun and the moon's interactions with the oceans of the earth, which causes large bodies of water to move to and from coastlines with periodic cycles. So actually these tidal currents are predictable, very predictable, months or even years in advance, which is one of the driving factors for tidal generation. Many different technologies for extracting tidal energy from the tidal phenomena have been proposed in the literature, but the main focus of the development has been on horizontal axis tidal stream turbines. The driving factor for this is that these turbines are very similar to wind turbines, and therefore they can be modeled in a very similar way to wind turbines. The main difference, therefore, for dynamic analysis of power systems between tidal and wind generation will be in the flowing mass that produces the generation, that is, in the wind speed and the tidal current speed. In these figures, we see measured 10-minutely averages of tidal current speed and wind speed. And the tidal current speed has these periodic peaks, which are very predictable, which makes it, in this time frame, way more predictable than wind speed. However, both wind speed and tidal current speed are subject to short-term variations in the time frame of seconds to minutes. In the case of wind speed, these are due to turbulences and gusts. And in the case for tidal current speed, it's due to turbulence and also waves that may affect the tidal current speed in certain locations and times. And this is what we want to be able to model, these short-term variations. So for the stochastic modeling done in this paper, we use stochastic differential equations, or SDEs. Specifically, to build all of the stochastic models, we use Ornstein-Uhlenbach SDEs. And an example of an Ornstein-Uhlenbach process is shown in the equation here. An Ornstein-Uhlenbach process is mean reverting and Gaussian. To build more complex stochastic processes that are, for example, a combination of faster and slower dynamics, we use the superpositioning of Ornstein-Uhlenbach processes, as is shown in the lower equation here. And the stochastic models used in this case study are for modeling the loads, the winds, and the tidal generation. So for modeling loads, we use the well-known voltage-dependent load model shown in the top two equations here, with the inclusion of a stochastic component which models the stochastic variations in the load. The stochastic component are two Ornstein-Uhlenbach processes, which are the two lower equations here. And for this case study, the uncertainty of the load is set to be 10% of the nominal load power. For modeling the wind speed, we use this for each of the wind farms. We use this model which is composed of these two parts. That is the mean wind speed, which is modeled as a constant, and a stochastic process. The stochastic process is Gaussian and a superposition of three Ornstein-Uhlenbach processes. The parameters for this stochastic model are based on previous data analysis. And the stochastic model also takes into consideration the damping of the blades and the aggregation of the full farm. And finally, to model tidal current speed, we model it in three different parts. We model as the predicted tidal current speed, which is modeled as a constant, and then we have a stochastic component which models the stochastic turbulence in a similar way as we saw earlier for wind speed. And finally, we have a wave component that models the effect of waves on the tidal current speed. This is modeled using a Stokes model coupled with the Jónsdóttir spectrum, which enables modeling different wave scenarios affecting the tidal current speed. And for the case study, we use a system model of the Irish system. The Irish system is a relatively small, isolated transmission system with two HVDC connections to Britain. It's operated by two different transmission system operators, namely Sony in Northern Ireland and EirGrid in Ireland. And the system model we use is composed of 1,479 buses and 169 wind power plants. And the wind power plants are supplying 25% of the generated power. Now for the inclusion of tidal generation into the system model. Ireland actually had the first commercial scale tidal stream generators located in Northern Ireland as a part of the CGen project. This project gave very valuable information about the future development of tidal generation in Irish waters. Then in 2010, a study was conducted to find the potential tidal generation locations across Ireland. Multiple locations were defined, but the locations with the highest potential are shown here, the 4 locations, and this is where in the system model we will install tidal generation. And their combined generation is set to supply 10% of the total load. And for the case study, we consider these 5 different scenarios for the Irish system. For the first 2 scenarios, we have 25% onshore wind. But in scenario 1, only the loads are modeled as stochastic, and then in scenario 2, the loads and the wind are modeled as stochastic. For scenario 3, only 50% of the generation is supplied by onshore wind, and the remaining 10% is now supplied by offshore wind, where offshore wind power plants have been installed in the potential tidal generation locations shown in the previous slides. And still loads and wind are modeled as stochastic. Then we have the 2 remaining scenarios, scenario 4 and 5, where we have 15% onshore wind and 10% tidal generation. And in all of these, in both scenarios, the loads, wind and tidal are modeled as stochastic, but the difference between the 2 scenarios is that scenario 4 is modeled where waves are not affecting the tidal current, and scenario 5 is where waves affect the tidal current speed. And now for some simulation results. So in this figure, we show the standard deviation of the ramps in the center of inertia frequency of the system for the 5 different scenarios and a measured data set. The measured data set is frequency measurements from the IRIS system for a case where there's not really any wind supplying the generated power, so the stochastic variations in the frequency are mainly due to loads. And this is why the measured data and scenario 1, where only the loads are modeled as stochastic, show us very similar frequency variations, except maybe in the time frame between 10 and 20 seconds, where the measured data shows higher variations in the frequency. And then we have scenario 2, where the stochastic like the wind is modeled as stochastic, and we see slightly higher frequency variations. And then we have finally the 3 remaining scenarios. If we compare scenario 3 with offshore wind and scenario 4, which has tidal generation with no waves, we see that the tidal generation gives us slightly lower frequency variations. However, when the tidal generation is subject to waves, the frequency variations for tidal generation get bigger. And that's why we decided to look at more different wave scenarios that might affect the IRIS system. And all of these scenarios are based on actual measured records of the wave heights and the wave periods in the IRIS waters. So we have these 3 different scenarios that we consider. Scenario A, which we also saw in the previous graph, where all locations are modeled with small waves. Then we have scenario B, where 2 of the locations are modeled to have small waves. These are the locations that are located in the IRIS Sea, and then 2 of them with medium waves. And then finally scenario C, where 2 of the locations are modeled to have small waves. 1 is affected by medium waves and 1 with large waves. And this is the extreme case. And as we can see, for the bigger wave scenarios, we are seeing larger frequency variations to levels that are not acceptable in the system. And this is why we decided to test installing frequency control of the tidal generation. And again, we utilized the fact that the tidal turbines and the wind turbines are in many ways similar, and we use a frequency control that was designed for wind turbines for the tidal turbines. This frequency control is composed of droop control and rate of change of frequency control. And we can see that installing this frequency control actually enables us to mitigate the frequency variations due to the waves to acceptable levels. And just for comparison, we also show scenario 2 and 3, which are only composed of wind, and the frequency variations due to the waves are quite close to these scenarios. And therefore, to conclude, this paper shows a comparison of the effect of wind and tidal generation on the frequency variation in the IRIS system. And we see that tidal generation does not necessarily introduce larger frequency variations in the system, except in cases where waves are present and affecting the tidal current. And the frequency fluctuations introduced by these waves can be successfully mitigated by including tidal turbine frequency control. So thank you. Any questions?
Thanks, Margrét. Very nice presentation. I see already one question, and whenever it comes to dynamic models and dynamic behaviors, I know that Petros Aristidou is always interested into it. So he has a double-part question. If you would like, I will read it, and if you would like to respond to it. So
I saw it.
Okay, but you need to read it loudly.
Yeah, you can just read it if you want.
Yes, I will read it. How were the tidal location and their parameters used in the SDE identified? So this is the first part.
I think I will answer the second part as well, because
okay.
the wave conditions. So the second part is there a study or historical measurement data available?
Yes.
So the SDE models are actually identified based on measured data from the Magen test site, which is actually in Scotland, north of Scotland. But the wave scenarios we consider are based on wave measurements, just like the historical wave scenarios in the seas around Ireland. And that is referenced in reference 25 in the paper. And the measurements for the Magen project are actually available as well from the test data that we build the SD models from. And these are referenced in the paper as well, but you'll have to find them. I think it's in the section. You'll have to find it. I'm sorry, I don't want to maybe be spending time trying to find the reference.
No, it's fine. Then you could maybe chat privately with Petros if there is a need to share a reference. Thanks for this. If Petros is unhappy, please continue with the Q&A, Petros. I would take a second, again, a double part question from Ihui Zuo. So first is for wind speed model. How do you differentiate the onshore with the offshore wind, and if you use real data? So please.
Okay, yeah, I'll start with that. So for the onshore, we just assume that there's actually a higher percentage of turbulence in the wind speed, and also the locations compared to the offshore. So like a higher percentage in the onshore turbulence compared to offshore, and the locations. So they're connected at these more remote locations in a bigger bunch.
Okay, and then the second part of the question regarding the power system model, how you model the Ireland grid?
So we actually got from the air grid to the TSO in Ireland a what is the software called? PSSC? Well, no, it's slipped my mind. The most popular power system modeling software, PSSC, and we converted to DOME, and it's there's further details on the model in the paper, but it has 1,479 buses, and yeah, it's just the model we actually got from the TSO in Ireland. Okay,
thanks. I see no more questions, so I would just have one brief question. Have you ever tried to, let's say, evaluate what is the limit of stability or frequency stability when you keep increasing your wind power productions and tidal? Of course, it's an hypothetical exercise, but did you try
we haven't actually done that yet, but that would be very interesting to do.
Okay, good. So I see no more questions. I'd like to thank you very much for this very nice presentation.